compute the radiation field, we have got all the information or all the mathematical background that is necessary for computing the radiation field. So we look at this. Now what we are going to do is we are going to find out the radiated field at far distance from the current, which is localized at one point. It is not a moving current. Current is localized one point. At one point, the current is J. It is localized, and from that location, localized means it is fixed at one point. It is time varying, but it is the location is fixed. So from that point, at a very far distance, we are going to compute the radiation field. So how we will get that? First is we obtain the radiation field using the radiation vector potential A. We have found out an expression for radiation vector potential A. So we will obtain the radiation field using the radiation vector potential A. A is equal to, as we have this found out, exponential mu exponential J K dot R divided by 4 pi R, then integration of J exponential JKR, volume integration of that is vector potential A. Then once we find out A, we can find out the curl of A. The curl of A, once you compute the curl of A, we will ignore all those terms which are falling faster than 1 by R. We will consider only the terms which are falling as 1 by R. So let us see what it is. Curl of A is equal to curl of mu exponential minus JKR by 4 pi R into A. Okay, that is equal to R cap. Now curl is equal to R cap dou by dou R plus the angular derivative. Delta is R cap dou by dou R plus all other angular derivatives, that is dou by dou theta, dou by dou phi terms are there. Now so that part, then cross product with mu exponential minus JKR by 4 pi R into F. So if I do that calculation, this will be R cap cross F. The first part is R cap cross F will be there. Then on dou by dou R of mu by 4 pi R exponential minus JKR. So that will give me minus JK. For the numerator term, it will give me minus JK. Then I have mu epsilon minus JKR by 4 pi R plus the terms which are of the order of 1 by R square or higher. So those terms we will neglect. The 1 by R square and higher order terms we will neglect. So this we can write as minus JK cross A. So a minus JK vector, because K, what is K vector as we have discussed? K vector, K is equal to amplitude of K or magnitude of K into R cap. So from the first term, if you look at the first term, it is minus JK R cap cross F. So K into R cap, that gives you the vector K. So minus JK, then cross K and K into F into the other terms, mu epsilon mu exponential minus JKR by 4 pi R. So that part is equal to your A, because A is equal to mu E minus JKR by 4 pi R F. So that part is equal to A. So this will be minus JK cross A. So that part will be this, the first term will be this, plus order of the terms which are 1 by R square, 1 by R cube, etc. So those will be there. Now now we will find out the angular derivatives. From this we will find out the angular derivatives. The source, for the source, theta and phi derivatives are in the gradient term. These will be in the gradient term, which means they will be operating only on f theta phi. If you are doing this, the angular derivatives, for the angular derivative, the source are theta and phi derivatives in the gradient term. They operate only on f theta phi. F theta phi already has a 1 by r factor in them. Therefore, the rest of A has another 1 by r factor, and so total will be 1 by r square or 1 by r cube. So those angular derivatives therefore will be neglected. So when computing, we are going to compute under the partial derivative of exponential minus jkr by r with respect to r. Then we'll keep the derivative of the numerator. Denominator will decrease as 1 by r square, so that will be neglected. In the denominator, that part will be neglected. Then use full rule to order 1 by r. Only we are going to get 1 by r is replace grad f theta phi exponential minus jkr by r. This we can replace as delta is equivalent to minus jk, or that is minus jk r cap. So for calculating the gradient, use this form. Then if you require to find out curl of A, for curl delta we are using minus jk, so that will be minus jk cross A minus minus plus j into j minus 1, and so that will be minus 1 into k cross A. Now change the order of multiplication, so that will be k cross A cross k. Minus will be going inside because the order of multiplication is changed. So that will give us, using the back-cap rule, this will give us k square r cap cross A cross r cap. So that we can write for k square, we can write omega square mu epsilon, that into r cap cross A into r cross r cap. Accordingly, you can find out what is E. E will be now minus jk eta exponential minus jkr by 4 pi r into r cap cross f cross r cap. H will be minus jk exponential minus jkr by 4 pi r cap cross f. Now if you compare E and H in terms of their magnitude, there is a difference of eta. So E is equal to eta H cross r cap, or H is equal to 1 by eta r cap cross E. Either of these two we can use later. So accordingly, we can find out amplitude of E by amplitude of H is equal to eta, or magnitude of E and H, the magnitude of E by magnitude of H is equal to eta. Eta is called the intrinsic impedance of the free space. So now once we do this, then we have to observe something. The observation is the radiated wave is similar to a uniform plane wave. Why it is similar to a uniform plane wave? If you look at this, the ratio of the amplitude of E and H of a uniform plane wave is eta. In this case also, for radiation wave, the ratio of E and H is eta. Therefore, the radiated wave is similar to a uniform plane wave. Then the second thing that we observe is E and H and r cap, they form a right-handed vector system. Just look at the expression for E. E is equal to eta H cross r cap. So E is perpendicular to H and r cap. Similarly, look at H. H is equal to r cap cross E. So H is perpendicular to r cap and E. Therefore, E, H and r cap, they form a right-handed vector system, or they form a triad. Then E is always parallel to the transverse part of perpendicular of A. That you can see from the first equation. E is equal to minus jkn, the jk eta that will neglect, exponential minus jkr by 4 pi r, these are amplitude. Then E is equal to r cap cross F cross r cap. Since it is r cap cross F cross r cap, therefore to the perpendicular part of F, E is parallel. So it is E is always parallel to the transverse part of a perpendicular of the radiation vector F. H is always perpendicular to the radiation vector F. Why? H is equal to r cap cross F into some constant. So since H is equal to r cap cross F, so H is always perpendicular to F. Then there is a DC current source which is happens for omega is equal to 0. Omega is equal to 0 means K is equal to 0. So if you have a DC current source K is equal to 0, then E is equal to 0, H is equal to 0, which means there will be no radiation. So there won't be any radiation at all. If you have a DC current source, you require an AC current source for radiation to occur. Now let us decompose the radiation vector. And this radiation field is like this. We have a source. For this source, we have the field F. F is decomposed into two components, F perpendicular and F are radial component and perpendicular component, or transverse component and perpendicular component. Then at the far field, we are observing the electric field, or the electromagnetic field. It has electric component and magnetic component which are perpendicular to each other like a plane wave, and it is propagating, the power is propagating in the direction r. So we have r cap in the radiated field. So if you take an elementary area that is subtending an angle d omega at the origin or the source. So F, we can write F is equal to, once we know this, we can write F is equal to r cap into r cap dot F plus r cap cross F cross r cap. That we can write as, if you expand that, that gives us r cap Fr. Fr is the radial component of F, then plus F perpendicular. F perpendicular is the perpendicular component of F. So F we can also write in spherical coordinate system as r cap Fr plus theta cap F theta plus phi cap F phi. So these are the two ways we can write F. So in terms of Fr and F perpendicular, and in terms of the radial potential, in terms of spherical coordinate system. Then we know r cap cross F. What will be r cap cross F? F has two components. R cap cross F, once you write F is equal to r cap Fr plus theta cap F theta plus phi cap F phi. The r cap cross F will be r cap cross r cap Fr, that will be 0, plus r cap cross theta cap F theta, that will be phi cap F theta, plus r cap cross F phi cap F phi. R cap cross phi cap is minus theta cap. So minus theta cap F phi. So r cross F will be given by this. Therefore, we can write the F perpendicular term. F perpendicular is r cap cross F cross r cap. So that we will write as phi cap F theta minus theta cap F phi whole cross multiplied with r cap. Phi cap cross r cap is theta cap. So the first term will be theta cap F theta. Then minus theta cap cross r cap is phi cap. So the second term will be plus phi cap F phi, which means only F theta and F phi terms, they contribute to the fields. So from the perpendicular, this we see that only F theta and F phi term contribute to the field, not the Fr term. Next. Now F, as we know, is equal to r cap Fr plus theta cap F theta plus phi cap F phi. R cap cross F is equal to r cap cross F perpendicular. This we have seen, and that this we have already seen. Next. Okay, for these two I am just repeated for remembering. Then E will be, we have seen the expression for E in terms of F and r cap. So E will be, now if you use these two terms, r cap cross F and the term, then E will be equal to minus jk eta into exponential minus jk r divided by 4 pi r. This part remains as it is. We are not changing anything in this. Then the terms of r cap cross F cross r cap, that gives us theta cap F theta plus phi cap F phi. So that part is there. Then H is equal to minus jk exponential minus jk r by 4 pi r into r cap cross f. R cap cross f is equal to phi cap f theta minus theta cap fp. So that we will put here. Now if I compare these two, I can say E is equal to minus jk eta into exponential minus jkr by 4 pi r into f perpendicular, because we have used that in finding out phi E. Similarly, h we have found out by taking r cap cross f perpendicular and dropping the a eta from E. Now, if I consider only f theta, then all linear antennas and arrays, they will contain only f theta. The z-axis will be in the direction of the antennas. So if the electric field has only f theta component, no f phi component, those are all linear antennas and arrays. They only have f theta component. The z-axis is in the direction of the antenna. The radiation vector components are r and theta. Okay. If you consider only phi component, we do not have a theta component but only phi component in the far field. Then these are loop antennas. The antenna is in the xy plane, the loop is in the xy plane. This is an example. Radiation vector components are r and phi. In the f theta it is r and phi. For f phi it is r and phi. Both f theta and f phi, with f phi is equal to plus minus j f theta. If you have this type of field component, that both f theta and f phi are present, where f phi is equal to plus minus j f theta, which means they are in phase quadrature, then the resulting electric field is circularly polarized. Example is an helical antenna. So with this, we come to the end of today's discussion. Now, I will request you to read this one carefully and remember these expressions for EH. If you don't remember anything from this class, no problem, except the last slide, E and H in terms of f theta, f phi. So remember E and H, expression for E and H in terms of f theta and f phi. You need not be asked in the examination, they will not ask you to derive this E and H in terms of f theta and f phi, but remember this. And we have to find out what is f theta and f phi for different antennas. That will do. F is the radiation vector. Remember, f is the radiation vector. So remember that it has three components, and f theta and f phi components we have to find out later. So with this, we come to the conclusion of today's class. Next class, we are going to discuss linear antennas, particularly half-wave dipole antenna. And if we will get time, we will do some simulation. Otherwise, at your free time, we will do some simulations. How many of you have got the HFSS? Now let us stop here. First, let us stop the presentation. Stop presenting. Now tell me, how many of you have HFSS? If you do not have HFSS or CST Microwave Studio, you can ask Okhida. From Okhida, you will get HFSS or CST Microwave Studio, in which we can do all types of simulations